So today we're going to be talking about exponential and logarithmic functions and their graphs. Okay, so these two are unique functions. Okay, the first thing, the exponential function f with the base a is defined as f of x equals a to the x. So a has to be greater than 0, a cannot be equal to 1, and x is any real number. Okay, so a can be like 1/2, it could be 2, it could be 3, okay? It has to be bigger than 0, okay, which means not negative, and it cannot equal to 1, okay, because 1 to the x power would just be 1, because 1 to any power is just 1, so that's basically the constant function. So the base has to be, it can't, bigger than 0, but not 1, okay? So for instance, f of x equals 3 to the x, and g of x equals 0.5 to the x, and f of x equals e to the x. These are all exponential functions. They all look the same, they have the same characteristics, okay? Their bases are just different, okay? So, when we look at this graph of a to the x, there are a few points that are going to be universal in all exponential functions. First one is all exponential functions, no matter what a is, when you plug in 0 for x, you get 1 as your y, because anything to the 0 power is 1. So right here, 0, 1 is always going to be a coordinate for every single exponential function. Now, then the next point that's going to be really important when we're doing this, okay, is going to be also whatever your a is, when you plug in 1 for x here, when x is 1, the other coordinate that you're going to be looking for, or when I check these, is going to be 1a. Okay? Because whenever you plug in 1 for x into the exponential, your y value is going to be whatever a is. So when you plug in 0, it's always going to be 0, 1. When you plug in 1, it's going to be 1a. So when we do graphs and transformations, those points are basically the only points that I'm going to be looking at. Okay? The other thing that all of these exponential graphs have is a horizontal asymptote at x. Okay? At y equals 0. Now technically, the other coordinate that we could actually use and find would be this coordinate right here at -1, which would be 1 over a, depending on what it is. So those 3 points right there are really the ones that I look for when I look at graphing the exponential. -1 when x is -1, when x is 0, and when x is 1. Okay? Now the domain for the exponential is from -infinity to infinity. It's all real numbers. The range is going to be from 0 to positive infinity. Okay? Now this is the parent function. This is without any kind of transformations. All right. And there's my horizontal asymptote at y equals 0. So these are the key features of any exponential function. Okay? So for example, if I'm looking at, say, 2 to the x, okay? And let's look at a chart. When I plug in -2 for x into my exponential, that's 2 to the -2 power. And we talked about this the other day. That negative power takes the reciprocal, and the 2 is going to square it. So when I take 2 and I take the reciprocal, I get 1/2, and 1/2 squared is 1/4. So that is my y value, -2, 1/4. This exponent here, when I plug in -1 for x, I get 1/2. When I plug in 0, I get 1. When I plug in 1, I get 2. When I plug in 2, I get 4. Okay? it's a really easy graph to graph as long as you know your exponents. And again, if we plot those points, we get this exponential function. And if you notice, again, 0, 1 and 1, 2, those are those two key points that we're looking for. Okay? Really easy graph. Now, E is a number. Okay? It is actually what we call Euler's number or Euler's number, depending on who you ask. Okay? But it is literally 2.71828 something or other. Okay? So again, though, when we look at it, we got those key points because 0, when we plug in 0 here for x, any number to the 0 power is 1. And basically 1 will give me whatever e is, which is 2.72828, blah, 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 which is basically close to 3. Just like a lot of people when we, mainly engineers, when they approximate pi, they approximate pi to 3 because it's 3.14. And a lot of times when we approximate e, we approximate it to 3 as well. We just move it a little bit closer to 3. Okay? But again, we get those same key points here at 0, 1, and whatever 1 is at basically here. Okay? Nothing too difficult. Okay? So this is our e, the irrational number e. So e is approximately 2.718281828. Okay? And just like pi, it goes on forever and ever with no repeating. Okay? Basically used in models for like growth and decay. One of them you learned in Algebra 2, which was the interest, compounding interest continuously. So when you take your interest calculation here and you say, oh, as the number of times you calculate that interest goes to infinity, an infinite number of times, you end up with this number e. Okay, and that's where you get that equation p equals e to the rt, that PERT equation. Oh. Well, we'll talk about it this year then. Okay, so considering this, f of x equals a to the x, this is a one-to-one function. Okay, so therefore it has an inverse function, and its inverse is called the logarithmic function. So we talked about this yesterday, how you change a logarithm to an exponential, but we can also talk about how to change an exponential to its logarithm form. It goes both ways. So when we look at this, we can see that these common things, these common ideas that we use for the exponential to graph it, we're going to be using for the logs. So of course the most common are log base 10, that's why we call it the common log, and e, which is the natural log. So y equals ln x is called the natural log function. Okay, and I just wanted to make sure that we went over that again. So here we go. The logarithm function with base 2. So we did the exponential 2 to the x power. Okay? That's the green line right here that we just did. Okay? Y equals x, when we talk about inverses, graphically, inverses are reflected over that line y equals x. So this purple line right here represents my log function of log base 2, which is the inverse of my exponential of 2 to the x. And you can see that it is, in fact, when they're graphed, are actually reflections. If you took that and folded it over the y equals x, they are identical. They reflect perfectly over that line. And looking at their equations and plugging points in, this equation right here, y equals 2 to the x, when I plug in -3, I get 1 over 8. So that means its inverse is 1 over 8. When I plug it in, I get -3. So you can see how the ordered pairs are even switched, because when you find inverses, you switch x and y. So where the domain of my exponential is all real numbers, that means the range of my inverse is all real numbers. Where the domain of my exponential is from 0 to infinity, the domain of my inverse, which is the logarithm, is 0 to infinity. And if you remember, in the exponential, it has a horizontal asymptote here at y equals 0. That means its inverse has a vertical asymptote here at x equals 0 because they reflect. So where the exponential has a horizontal asymptote, the logarithm has a vertical asymptote, which is going to be important in just a minute because you can't plug negative numbers into a logarithm. Okay? Because the domain is from 0 to infinity. So you can't plug in numbers that are lower than 0 unless there's been a transformation applied. Okay? So here we go. Looking at just the graph of the logarithm, just like the exponential, we have, instead of that point 0, 1, we have this point 1, 0. Okay? And just like that point where we had in the exponential 1 and then a, in the logarithm, we're going to have whatever a is, 1. Because remember, they switch. And that's one of our identities. If we actually plugged in the log base a of a is 1. That's one of our identities for the logarithms. So that just goes to show this coordinate a1. Okay? So you can see very easily, again, on this one, there's only 2 really key points that we're going to be looking for. Okay? And of course, the natural log basically works the same way as the exponential does to the log base a, where e to the x and ln x. Okay? And that is graphing logarithms and exponentials.